So good afternoon, everybody. We start the session, the last effort by Markus Diehl in this school. Please, Markus.
Thank you, Raj, Sergio. So today I would like first to speak about transverse momentum-dependent distributions, TMDs. I will focus on certain aspects, and you will hear more about these functions in Barbara Pasquini's lectures later this week. And in the second part today, I will tell you a little bit about double parton scattering. So we have in the last lectures seen and discussed the ordinary parton densities, which give us information about the longitudinal structure of a hadron, and we have generalized that concept to processes with momentum transfer, which allowed us to make statements about transverse position of partons. Now, TMDs look at another aspect, namely they look at the same time at the longitudinal and at the transverse momentum components of a parton inside a hadron. And that is important in processes where the transverse momentum of produced particles is measured. One example is the Drell-Yan process, where one measures the transverse momentum of the produced virtual photon. Of course, that is measured by the sum of transverse momenta of the two leptons it decays into. What I will focus on for the moment is the case where that measured transverse momentum is small compared with the large scale in the process, which is set by the virtuality of the boson. Another process where the same concepts apply is semi-inclusive DIS, SIDIS. I haven't discussed that in the third lecture. That was something I had to skip because of time. So if you're interested, you can look up the slides there. So I will now just give a brief account of what semi-inclusive DIS is about. In semi-inclusive DIS, we measure the cross-section of the scattering of a lepton, which in this graph is omitted as usual. The lepton is deflected and radiates a virtual gauge boson. That scatters on the proton target. And then the measurement singles out a single hadron in the final state and sums over anything else. So it's a one particle inclusive and in that sense, semi-inclusive measurement. And in appropriate kinematics, namely again in the Bjorken limit, and in the case where that hadron moves in the hemisphere of the virtual photon rather than in the hemisphere of the incoming proton, then we have again a factorization. The process then can be factorized into a parton distribution, as is written at the bottom of this graph. A hard scattering, which I have sketched here just by its lowest order, photon scattering a quark. And then here is a new non-perturbative ingredient, which is called a fragmentation function. So this is very closely related to the concept of parton distribution function, only that in the fragmentation function, you start with a parton. And in that parton, so to speak, you look for a particular hadron. Perhaps a better way to say is we look at how a single parton hadronizes into a specific hadron which is measured, of whom we know and can measure the momentum, and if it's polarized, also its polarization, and anything else. And the anything else we don't care about, just as we do not care about the anything else which is remaining when we extract a single parton from the proton, as it's described in parton density. So a process where two such fragmentation functions would come in is the plus and minus annihilations in two measured hadrons which have approximately which have approximately opposite momenta with a small relative QT. Then the underlying factorized process here is that you have a virtual gauge boson going into QQ bar. and the QQ bar, each of them hadronize into a hadron, and as usual, you have the remainder of the final state, and in this case, you have two fragmentation functions. So transverse momentum dependent distributions come in if the transverse momentum that you measure in this case here is the transverse momentum of the outgoing hadron in a frame where the, say, the virtual photon and the proton have zero transverse momenta, such that the transverse momentum of this measured hadron can be thought of arising on the one hand from the small transverse momentum that a parton carries inside its parent hadron, and from the small transverse momentum that it distinguishes the outgoing hadron here from its parent quark during the hadronization process. So for the purpose of organizing our scales, we count the transverse momenta in this graph as of the same order as other non-perturbative quantities like hadron masses. And the big scale is as before given by the virtual photon the photon virtuality. In such a case, when we compute the hard scattering, since that is dominated by the big Q squared, we can still set the parton KT to 0 because it's a correction to the big scale. Now that doesn't look like much in this very simple example here where it's just a tree-level vertex, but if you start dressing this with virtual corrections, it is really important that you set the transverse momenta of the partons in the hard subprocess to 0, as we would do it in the usual factorization we discussed so far. The thing that we don't want to do now is in the parton densities and in the fragmentation functions, we no longer integrate out the degree of freedom, which is the transverse momentum of the parton. We did that before in the lectures so far because that transverse momentum wasn't relevant for the measurement, and it just could be integrated out at the level of the parton densities. Now, since the transverse momentum determines something we measure in the final state, we no longer do that integral, and then our parton distributions become dependent on KT. Just as a matter of notation, in formulae, I will keep using this bold phase notation, so you know this is always a transverse vector. If it's in text and to give names to things, then I will normally put the KT because I also need to speak it. So in that case, we need KT bit dependent or unintegrated PDFs. Unintegrated just means you don't do that integral, which you would normally do. And these kind of distributions are normally called TMDs. And this term is used in a wider sense. It also extends to KT-dependent fragmentation functions, which you would have here. And if we have still a factorization between short and long distance dynamics, that is called TMD factorization. And we will see in this lecture that it has common aspects with the usual factorization discussed so far, but it also brings in new aspects and differences. Now, just to give you an idea of data that is relevant in this context. So I mentioned Drell-Yan production with measured transverse momentum of the boson and semi-inclusive DIS. Now here are some transverse momentum spectra from semi-inclusive DIS measured at high energies at Hera quite a few years ago. That's electron, proton gives electron, any charged hadron plus anything else. It happened that the measurement that could best be done with the H1 detector was for charged hadrons, but without being able to tell whether that was, for example, a pion or a kaon or a proton. So this is summed over these possibilities. And you see how such a spectrum typically looks like. It's very steep. Note that this is a logarithmic scale here. The transverse momentum falls off very steeply as you go from small to larger values. This here is the momentum spectrum, the transverse momentum spectrum of the lepton pair in Dwell-Yan process measured at the LHC at 13 TeV, center of mass energy. Excuse me. Note that here the PT of the Z boson is plotted on a logarithmic scale. There is a peak in this spectrum, which you can also sort of guess at not such a good resolution in this case. That peak comes from the fact that the cross-section here is differential in PT. When one does the calculation, one typically finds the cross-section in dpt squared, because that's the natural integration element for a transverse vector. D sigma by dpt squared is finite for pt equals 0, and then if you turn that into d sigma by dpt, the 0 that you see here is just a consequence of the Jacobian. So how would we treat such KT-dependent parton densities in field theory? Well, this here is a recap of what we have for the KT-integrated case. That is the type of matrix element that I discussed in quite some detail before. And if you want to have the KT-dependent analog, what you do is here one sets Z equal to 0. We no longer do that now, so we consider the quark fields at a certain minus component, minus position, and a certain transverse position. The plus component is still equal to 0. And we perform a Fourier transform with respect to that, and that corresponds then to the transverse momentum of the parton. So rather simple and intuitive. You can check if you integrate this quantity over all KT, what happens? Well, the only place where KT appears is in this Fourier exponential. Integrate over it gives you a delta function for the transverse vector Z. Then you can carry out this integral here, and you end up with Z being equal to 0, and that's exactly what you have in the first line. So the fields now are not only at different light cone positions along the light cone, they're also at different transverse positions. For the Wilson line, that has some important implications, which I will discuss later. Notice also that I've split here the Wilson line, which goes from the position of the quark field at Z minus to the position of the anti-quark field, which is sitting at 0 here, in such a way that I first run to infinity and then from infinity back to 0. The same I do here, but here at infinity, there's an extra piece that carries me from the transverse position Z to the transverse position 0. And again, I will come back to this detail later on. So an important aspect of such distributions is that you have more degrees of freedom and the possibility of correlations. Since now this matrix element depends on a transverse vector, you have singled out a direction in the transverse plane, and that brings in correlations with the spin. In this case, it is the spin of the parton the spin of the proton target that you consider. So this here is now no longer integrated or averaged over the spin of the parton. It depends on the spin, and if it's transverse, you have this type of cross product between K and S in the transverse plane. And the function that multiplies this is the Sivers function. We will come back to that a little later. If you average over the spin, you get back this function here, which is the direct analog of the KT integrated one. So if one looks more closely at the spin degrees of freedom, and I suppose that Barbara will tell you more about that, there's a whole zoo of distributions. So if one looks at the possibility for collinear or KT integrated distributions in a spin 1/2 target, we have 3 of them, which corresponds to the discussion that Barbara gave yesterday for generalized parton distributions. You have unpolarized partons, you have longitudinally polarized partons, and you have transversely polarized ones. which in each case here are correlated in these distributions with the corresponding polarization of the target, that is of the hadron. So if one goes to KT dependence, one has the same type of distributions as above, only depending now on KT. And one has these extra correlations between different vectors, the Sivers function I just discussed. There's another one which correlates the spin of the quark, not the spin of the proton, with KT. And there's a bunch of more densities, which I will not discuss here. And the analog can be done for fragmentation functions. In particular, if the observed hadron is unpolarized or has spin 0, then you have two of such distributions, one for unpolarized quarks fragmenting and one for transversely polarized quarks that fragment into an unpolarized hadron. And that here is called the Collins function. So how does TMD factorization look like in more detail? And I'll take as an example semi-inclusive DIS. The discussion then can be generalized to Drell-Yan process rather easily. So as I said, we take Q large, photon virtuality, and the measured QT small of the same order as other small scales that we neglect, like the hadron masses. So we have transverse momentum dependent distribution fragmentation functions. If you look at the hard scattering, you now, it turns out, only have to consider virtual corrections. So this here is representing the sum over all graphs starting from the tree level and then dressed by vertex corrections. However, what you do not have is the emission of hard partons into the final state, which you would have in ordinary factorization. Why do you not have that here? Well, if you emit a parton from a hard scattering, in order for the scattering to be hard, the parton needs to have a large KT. But if you start from a parton with a low KT, you radiate something with a large KT, then afterwards you have a large KT. And that would mean that the hadron that you observe then has a large KT, and that's not the region which we're looking at. So high KT radiation from the hard scattering is forbidden here. And if one looks more closely, that restricts us to virtual corrections, because the real corrections would inevitably produce large recoils in PT. So there is another important difference for the factorization, which we haven't had so far, and that is that we also have to take into account soft gluon exchange between the particles that move in one direction. These are the particles in the collinear distribution, in the collinear factor moving along the proton. These are all the particles, the fragmentation products that move in the direction of the outgoing hadron. And these two directions are very different. So if you think about fast-moving particles moving in different directions, you expect them to scatter. Everything here is carrying color. So there is a scatter. In order for these things to roughly keep their momentum, the scattering has to be soft. So that means it's a low momentum exchange. And that is included in this so-called soft factor. So that in the sense that it doesn't depend on the details of what scatters here of what, is again a universal function. Since it's soft, it's actually non-perturbative, so it has the same status or a similar status as these distribution functions. It's not something we can compute in perturbation theory. Now, why didn't I discuss this before? The reason is, if you integrate over the observed KT and turn your distributions into KT integrated distributions, it turns out that there is a cancellation between the effects of real emissions. That's one gluon here, a soft gluon that's emitted into the final state, and virtual corrections, which is soft gluon exchange that doesn't appear in the final state. So that cancellation happens exactly in the KT integrated case, and then this extra factor is 1. You don't need to talk about it. However, if you keep KT in the final state fixed, then you still have to integrate over all possible virtual exchanges, but the real exchanges here are restricted because you observe the KT of the hadron, and that means the KT that goes into the final state here is no longer unrestricted. Then the previously happening compensation no longer happens, and the soft factor is non-zero. So how does a factorization formula look like in such case? So let's now look at the virtual photon-proton cross-section, differential in the transverse momentum and also in the momentum fraction of the hadron with respect to the fragmenting quark, that's called Z. There's a kinematic factor from phase space and such. There's the square of the hard scattering amplitude. And then there is an integral over transverse momenta of the unobserved partons here, the partons coming out of the proton, the parton that fragments, the partons that are exchanged in a soft scattering. And they have to collaborate to give you the observed transverse momentum Q of the observed hadron. And then you have the distribution, the fragmentation, and the soft factor. Now, notice that because the parton distributions here don't have an integral over all KT, that implies that they have no D-glab type evolution equation. If you remember how I explained why ordinary parton densities have follow D-glab evolution, that's because you integrate them over KT, but you should take out the ultraviolet part of that integration. That's what D-glab describes. If you don't integrate over KT, but limit it to small values, then there is nothing to be renormalized or cut off. And therefore, D-glab type evolution simply does not happen for these KT-dependent factors. Now, this here is an integral over 6 variables that tie together these 3 functions. That is rather awkward. And you can simplify that greatly if you perform a Fourier transform for each of the functions from the transverse momentum to a Fourier conjugate position, which conventionally is called B. Now, unfortunately, somewhat, this B is not having the same status as the variable B in generalized parton distributions that was discussed yesterday. And later on, I will call the B in this context of TMD is Z, but in the TMD literature, people typically use B. So you shouldn't be surprised and just be aware that it's a different type of variable than the one in generalized parton distributions. So this here is a nested convolution integral if you take a closer look. And you know that convolution integrals, if you Fourier transform, the integrands turn into a standard ordinary product. And that's what you have here. So rewriting this gives us the product of the now transverse position dependent distributions. And what remains from this delta function here is an exponential that is a Fourier transform of these B-dependent functions with respect to the observed transverse momentum. You can again see what happens if you integrate this over Qt. Then this here turns into a delta function for B equals 0. You get back these functions at B equals 0. B equals 0 in the sense of the Fourier transform corresponds to integrating the original momentum space functions over all transverse momenta, and that would be the collinear factors. So you see that the circle, you come full circle at this point. Now, something awkward for phenomenology is that you have now a distribution and a fragmentation function and another non-perturbative function, which you have to try and all extract from a limited number of processes. That's actually not so helpful. And in order to limit the number of unknown non-perturbative quantities, it is useful to redefine the distribution and fragmentation functions each absorbing, roughly speaking, part of the soft factor in the sense of square root of the soft factor you put here, another square root you put there. That's a little bit oversimplified, but for our purposes, it's good enough. So now comes another bit of a story. It turns out, well, TMD distributions have another dependence on what is called a rapidity parameter. And there is an evolution equation in that rapidity parameter, which is called the Collins-Soper equation, which has this form. D by d log of the rapidity parameter is given by a kernel, an evolution kernel, times the function itself. So there is no type of x integral here. And at the same time, you have an ultraviolet renormalization scale, which comes with an evolution equation that just has the form of an ordinary RGE, like for a hadron mass, like for a quark mass, as you've seen it in the first lecture, with a different anomalous dimension here, which is dependent itself on this rapidity parameter. So all gets a little bit complicated. We'll see a little later today how we can understand what this rapidity parameter means. But roughly speaking, it means that inside this function, what you want to have are partons that move more or less in the same direction as the proton. Because that's how we set up the factorization. Turns out if you just write down the matrix elements of operators between proton states, these matrix elements don't actually tell you that that every parton here should move roughly along the direction of the proton. The naive definition includes the case where partons move actually in the opposite way. But a parton that moves opposite to the proton shouldn't be inside the distribution function. It should be somewhere else in this factorized picture. Now we had a similar story for the KT. Defining the matrix element naively, you would integrate over all KT, and we had to use dglap. We had to use renormalization of the KT squared integral in order to make sure that you only keep the small transverse momenta in here. So a similar thing happens at the level of rapidities, and therefore you have this extra parameter. I will not discuss this coupled set of evolution equations in detail, but one important thing, and by the way, you can then look at what is the dependence of this anomalous dimension and of this Collins-Soper kernel here on the remaining variable. Turns out they are the same, and they're given by yet another anomalous dimension. And that they are the same follows from the consistency that if you take this log zeta derivative of log square root of zeta derivative of the second line, you should get the same as the log mu derivative of the first line. So this is just expected. And the nice thing about this set of differential equations is it's very simple to solve. And I won't walk you through the solution, but instead just write it down here. This is an exponential of something that is constructed from the different kernels and anomalous dimensions here. And it involves logarithms, as you would expect, because the variables of differentiation were logarithms. This here is what is called a Sudakov factor. And the logarithms that you get, the logarithms between different scales that you get when you evaluate these expressions in more detail, they are called Sudakov logarithms. You can anticipate that these are double logarithms, because here you have essentially d of log mu, and here you have another log mu, so that will give you something like log mu squared if you do the calculation. And this is exactly the type of double logarithms that I discussed in the lecture on E plus E minus annihilation. These double logarithms come from the combined region of collinear and soft integration, and they appear in a rather general context. In many cases, when you radiate soft or collinear particles, and here is just one incarnation of that physics. And it's also something that I anticipated in the earlier lecture. The way to sum such large logarithms to all orders typically is by writing down appropriate differential equations and then solving them. And that's exactly what's been done here. So let us confront this type of factorization with another type of factorization in the CDIS process, which is relevant when the measured transverse momentum of the observed hadron is large, of the same order at the large, as the large scale Q squared. In that case, how can you get such a large transverse momentum? Well, you get it from a hard scattering, because the fragmentation process and partons inside the hadron do not involve large transverse momenta. So if you want this to be a large QT, what you need in the hard scattering is the emission of at least one parton that gives you the recoil to this observed large PT. That was exactly what we vetoed and did not allow in the KT dependent case for small KT. And this is why here we couldn't allow real radiation. Here, on the opposite, we need the real radiation in order to have a large transverse momentum measured. And then you have again a type of collinear factorization with a collinear distribution function, a collinear fragmentation function, a hard scattering process which depends, which describes this process here, which now starts at order alpha s, because as I said, at least one parton must be emitted. And you have the usual convolution in momentum fractions, because the momentum fractions of this and that can compensate themselves such that you have a certain momentum fraction of the outgoing hadron, but they are not fixed by the process kinematics. And this is why you have integrals here. There is one kinematic constraint between the momentum fractions and the observed final state, and how this comes about is a bit more lengthy kinematic calculation, which I will not show you here. So now I would like to look a little bit more into a theoretical aspect of factorization, which in fact is important both for collinear factorization and for TMB factorization, which I've glossed over so far, but which was also mentioned yesterday in Barbara's lecture. And that has to do with these Wilson lines. So let's, for the moment, go back to the ordinary inclusive DIS with ordinary short distance factorization, and think a bit about exchanging extra partons between the collinear factor and the hard scattering. Now, generically, putting here extra exchanged partons will lead to a power suppression. And why the exchange of extra partons is suppressed is not so difficult to see, because if you think of having just the exchange of a quark and an antiquark, then you have this Handback graph at lowest order with just one off-shell parton up here. If you add another gluon or more of them, then you have more and more internal propagators in this hard scattering. And an internal propagator, depending on whether it's a fermion or a boson propagator, scales like 1 over the hard scale or 1 over the hard scale squared. And it must be the hard scale because that's the only quantity which the hard scattering is allowed to depend on. So more propagators mean higher powers of 1 over Q, and that is a penalty in the region where Q is large. But there is a way to circumvent this suppression from more propagators, and that happens if the polarization of the gluon that comes here from the proton side is along the plus direction. So how can that be? Well, let's think of a single gluon exchange here, and let's look at the associated pair of Lorentz indices mu here and there. You then have the hard scattering, which depends on mu. And since the hard scattering involves only large momentum components, all components of this hard factor are generically big. In particular, both the plus and the minus components of H are big. And that's because you have a momentum coming in here. That is this Q momentum. And if you remember the exercises we did earlier in the lecture, both Q plus and Q minus are large, of order Q. On the other hand, we have here this collinear factor B, which now has also a polarization index for that one gluon. Since it's a collinear factor, this dependence here can only be behaving like a collinear momentum vector, because that's the only thing that this factor is allowed to depend on. So it can depend on, it depends on the proton momentum, the momentum of the emitted quark, and the momentum of the gluon, but they are all equivalent in the sense that they are all collinear momenta with large plus components and small minus and transverse components. And therefore, if you multiply together the two factors, the only big factor that you have, or the biggest factor that you have, is a minus component here and a plus component there. And the plus component here corresponds essentially to having an A plus polarization of the gluon. Now, it would be terrible if we had to compute this explicitly for any number of gluons, because if there is no penalty for one gluon, there is no penalty for n gluons. And that sounds like a terrible complication, because you would need an extra distribution function for all cases where you have so and so many gluons here, and you would need to compute this hard scattering for all cases. That would be awful. But fortunately, there is gauge invariance in the form of Ward identities, which helps us. Now, if you use this proportionality here, then that means when you contract the hard with a collinear factor, contracting the momentum of the gluon with this factor here allows you to use a Ward identity. And that relates L dotted into H with essentially H, but with a gluon taken away, which is the hard scattering factor that we had for a single quark and anti-quark attachment. So that's very nice. And it turns out if you do this kind of calculation, what you have on the distribution side is a sum of distributions that is written at the operator level in terms of this path-ordered exponential or this Wilson line. So exponential is here, and the important ingredient here is that you have the coupling constant, the strong coupling, and this A plus field. And the details of this I will not discuss here. And this is how in collinear factorization, if you just look very carefully at all the graphs that you should take into account, this is how you get the Wilson line inside the definition of the parton density. So this is in a very explicit way of seeing how the Wilson line arises. A more indirect way is to say, well, without the Wilson line, the product of this quark operator at one position and the anti-quark operator at another position is not gauge invariant. And that's not a physically meaningful quantity in a gauge theory. So in order to make this a gauge invariant quantity, you need a Wilson line in between. What that general argument doesn't tell you is along which space-time path does this integral actually go from one to the other position. And if you want to know what the path is, namely here, it's just along the light cone, then you have to do this kind of explicit dynamical calculation. So this looks like something which only specialists need to know, and to some extent that's true. But now let's look what happens in TMB factorization. So again, we have this exchange of extra gluons. And it turns out, so this here is for the CDIS process, this is for the corresponding process in Drell-Yan production. And also the gluon exchanges here will now lead to Wilson lines, both in the quark distribution and in the fragmentation functions. But there's a difference physically. These extra gluons here are all coupling to the Struck quark. That means after the hard scattering, whereas in the Drell-Yan case, all these gluon attachments happen before the quark and antiquark annihilate, before the hard scattering. And it turns out this determines the path of the Wilson line in space-time, which now has to also have a transverse component, because the transverse component of this and that field are different, as I said earlier. And if one walks through the calculation, one finds that the paths you get are what is often called staple-like. So if this here represents the minus direction of the position, and that is one of the transverse directions, you start from some value here, you go along the light cone all the way to infinity plus infinity. Then you have this transverse piece, and then you go all the way back to here. In the Drell-Yan process, almost the same happens, except that you don't go to positive infinity in space-time. Instead, you go to negative infinity in space-time and go back. So the staples here are actually not the same. And this positive or negative infinity in Z minus is actually corresponding to you having, so to speak, final state interactions here and initial state interactions there. So at this point, an important remark. Barbara told you yesterday the Wilson lines in the ordinary PDFs, and therefore also the Wilson lines in ordinary GPDs, you can make them disappear if you take the A plus equals 0 gauge, because then this here is 0 and the exponential of 0 is 1. That looks like very simple. What happens if you try to do the same thing in this case here? It turns out that the light cone gauge, for all its nice properties it has, also has some not so nice properties. And that is in the light cone gauge, there is actually a non-zero effect from this extra piece along the transverse direction at light cone infinity. So in a sense, using the light cone gauge for TMDs is possible, but it's very tricky, because if you're not careful in what you're doing, you might miss these contributions from positive or negative infinity, and then you get the physics wrong. Which is why, for most practical purposes, in the TMD context, people prefer to use a covariant gauge where that subtlety is not there. So at this point, I want to show you another little calculation. And that is, I made all these statements here about gluons giving Wilson lines, but it's actually not so difficult to see how that happens if you look at the single gluon exchange case. So let me at least sketch how that calculation is done. So let's look at a part of the process. So we have the incoming quark, the hard scattering. This is momentum Q coming in. And let's just consider the case where there is one extra collinear gluon. And for the sake of simplicity, I put my final state cut here. There's another graph where the gluon attaches on the other side of the final state cut, which I don't even bother to draw here. Well, I could draw it like this, but this I will not compute now. So this is part of the answer that we need to compute. Let's call this momentum incoming L, and that here K minus L, so that the total incoming momentum is K. And of course, the total outgoing momentum in the final state is K plus Q. And as I said, I'm just interested in computing the left-hand part of the cut, so the right-hand part I can erase again. So what's the expression of this part of the graph? Well, the outgoing quark corresponds to a spinner at k plus q. Then we have a vertex here. So that's a minus Ig, a gamma matrix. And the gamma matrix of this vertex is to be contracted with the A field coming from below. Now I want to consider an A plus field, and that means the gamma Lorentz index of the gamma matrix is the minus. Yeah? So this would be multiplied with the A plus somewhere below in the matrix element, which for now I don't write down. And then this here is an outgoing on-shell particle, so it has no propagator, but this here is an off-shell particle and it has a propagator, and that I need to write down also. So it's K plus Q minus L. That is obviously the relevant form momentum, and that is to be contracted with the gamma matrix here. Now that's almost what I want to evaluate, but remember now that we said when computing a hard scattering graph, we should make the collinear approximation, and that is replace all incoming parton momenta with their collinear approximation, which I'll denote by a hat here. And for a right-moving particle, that collinear approximation means the minus component is set to 0 and the two transverse components are set to 0, and the plus component is just kept as it is in the original vector. And the same with L, same, I don't write it down. And that means when I compute this here in the collinear approximation, I just take the approximated momenta here. Any correction to this approximation is power suppressed and not part of my desired accuracy. So how can we simplify this? One way of simplifying this, so this is equal to is the following. I copy the spinner here, K hat plus Q. Now I have to be careful that I don't miss anything. So I have the minus Ig here, and I choose to divide that by L plus. And then I multiply it by L plus again, and the L plus combines with the gamma minus to L dot gamma on the condition of me putting the hat on the L. Yeah? Because L hat only has a plus component, so multiplying this out means L plus times gamma minus, and that's what I had here. And I still write down the propagator here. And now I make another simplification, or I take another trick. I write L hat as K hat plus Q minus K hat plus Q minus L. Just a rewriting. And if I plug that in here, I now can throw pieces away. The K hat plus Q times gamma acting on the spinner to its left, which has the same momentum, gives you 0 because that is the Dirac equation for a spinner. So the first term here I can leave out because it annihilates with a spinner, and I only need to keep the second term. Sorry, this here is a minus sign, which I forgot. But then in the second term, I have K hat plus Q minus L hat times gamma. And then that's exactly the momentum I have in the denominator of the fermion propagator. So this just cancels against the fermion propagator. And what I'm left with is the outgoing spinner and, oops, there's a factor of I and a factor of Ig over L plus. So this is obviously much simpler than what I started with. And you can also guess that it might be possible to use the same type of trick if I have multiple gluon exchanges here that will give just a repetition of such factors, and that's indeed what happens. But that's not what I want to show in detail here. There is one thing in this equation here which is too simple, and that is what should we do when L plus goes to 0? Because that's part of the integration I will have to do in the loop. And in order to understand what I should put here, what I should do if L plus goes to 0, I should write the fermion propagator in a bit more proper fashion, because what I did here this here was really meant to be I times K plus Q minus L hat times gamma in the numerator and the square of the 4 momentum in the denominator. And for a propagator, Feynman's prescription tells us what we are supposed to do when the squared momentum here goes to 0. Yeah. So let's see what that squared momentum is equal to. So it's, and again, we have these collinear approximations here. It's 2 times the minus component of this. Now, the only vector that has a minus component is Q here, because K hat and L hat are right moving. And then I have the plus momenta, and that is K plus Q plus minus L plus. And it happens that K plus Q plus is equal to 0. Now, why is that? That's because the final state quark here is on shell, and the on shell condition for this means, well, it has a large minus component, Q minus. In order for this to be on shell, we must have that the plus momentum, the plus component of this here is equal to 0. So the plus momentum of K hat plus Q is 0, and I'm only left here with L plus. So I should not even write down here this parenthesis. So that means I get a minus K plus Q minus L hat times the gamma matrix divided by 2Q minus, oops, sorry, minus here. And then I have an I divided by L plus minus I epsilon. Here I was a little bit too hasty. In fact, there is a minus in front of this here. So it's 2Q minus times minus L plus. Q minus is a positive quantity. Remember the exercises we did earlier in the lecture. So positive quantity times a negative sign for the L plus. That means if I pull out the Q minus with a minus sign here, I get L plus minus I epsilon. And that is therefore what is the correct prescription that I should apply in my simplification of the overall graph here. So that is the end of this calculation for the hard scattering. And now we should see how does this factor combine when I look at the matrix element at the bottom. So what we then have, so let me just draw the sketch here again. So when computing this, I will now omit all factors that are not essential for my argument, which of course in a full calculation one needs to keep track of. So we have this L plus minus I epsilon factor. L, coming from below here, is a loop, is an internal variable in a Feynman graph as soon as I put the collinear factor down here. And therefore L should be integrated over. And in particular, that means integrate over L plus, and of course also over LT. And then I need the expression here of my matrix element. Now we have some experience in how these expressions look like. We have integrals over the light cone positions of our fields. That is for the quark field. Now there is a corresponding integration for the gluon field. And for this, I write down both the longitudinal and the transverse part of the integral, because I need them in the simplifications to be done in the following. Then I have a big Fourier exponential. There's one exponential for the quark. And remember, the quark momentum here was k minus L. So this is k plus minus L plus times Z minus. Z minus is the position of the quark field. Then there is a corresponding quantity for the gluon, and that has momentum L. Therefore, there is a plus IL plus Y minus. Now I have to write down the same thing for the transverse positions. There's an over or minus which comes from this Euclidean, or from this Minkowski scalar product. The transverse momentum in a covariant scalar product, the transverse momenta always get a minus sign. Rather lengthy stuff to be written down. And then I have an IG, a minus IG, actually, I want to write it, times A plus. That's the A plus field, which we discussed earlier. And that's the only component that we're interested in. And the field here sits at light cone position Y minus and Y transverse. And there is the quark field sitting at Z. What I don't write for us in the arguments of the fields, just for brevity, is that Y plus and Z plus are always understood to be 0. And since they're always 0, I don't write that down. So this minus IG actually, if you go back, is what comes from this factor here. Somehow I apparently managed to lose a minus sign, which I will not try to track down right now. No, in fact, it's wrong. This here is a plus I. There we go. So that's just part of the matrix element at the bottom. There is also the outgoing quark field on the other side, but since I'm not going to touch that in the calculation, I don't bother to write it down. So this is a very lengthy thing here, but now we can start and make big simplifications. We have the transverse momentum integral over yt. The only place where yt appears is, sorry, no, we have a yt appears in many places, but we have a transverse momentum integral over Lt, and the only two places where Lt appear in the integrand is here and there. So the transverse integral over Lt gives a delta function which sets Zt, because there's a minus sign here, Zt equal to Yt. And then that delta function is carried out by the explicit integral over Yt, which is written here. Sorry for my rather terrible writing. Anyway, so that means this here and that here go away, and we will just set Yt equal to Zt in the remainder of the expression. What also remains is the integral over Z minus. In fact, I could have kind of left that out, but okay, let's write it down. There's the ik plus times Z minus, and another part of the exponent here was also not touched so far. That's the transverse piece. So this collects this piece, and then what is L minus dependent, L plus dependent is this here. There is an integral over d minus, dy minus also. That's this part, the 2 pi I put next to the integral over dl plus. And then the relevant part of the Fourier exponential is il plus times y minus minus z minus. And there is our factor 1 over L plus minus I epsilon. So if you have kept track of what we've written down, then the only thing that we haven't written down yet are the field operators. So there is the IgA plus. And as I announced, the transverse position of the A plus field is now the same as the transverse position of the quark field. But their light cone momenta along the minus, light cone positions along the minus directions are still different. Now here you see this Fourier transform of I over L plus minus I epsilon. This is something that you computed in the exercise classes this morning, and it gives you a step function in the Fourier conjugate variable, which in this case here is y minus minus z minus. So step by steps, we go from this terribly long initial expression to something which is much shorter. Actually, let's be a little bit economical. The whole first part here, this integral over z minus and this exponent, nothing happens to them. So I just copy them. And then I have an integral over y minus, which is now restricted because of the theta function, which we obtained from this here. And the restriction is such that I integrate this from z minus to infinity dy minus, and then I have Ig a plus of y minus zt times the quark field. So this was a bit lengthy, but the good thing is the final result is actually rather simple. I'm losing my pen here, which is not so good. So this here I don't need. So This here, if you look at the definition of a Wilson line, is what appears in its exponent if the Wilson line goes from z minus to plus infinity. And that's exactly the first term in the expansion of the exponential in a Wilson line. If you put more gluons here and much more work, then you will see that the multi-gluon terms all combine together to get the exponential of this expression here. And that gives you the Wilson line. And you see that just by doing the calculation step by step, we see also along which path the Wilson line must go. Namely, it goes from the position of the quark field all the way up to plus infinity. And that's in a way the important part of this calculation. We're going to make a break just in a little moment. I just want to wrap up this part of the argument, if you allow. So if one does the same part of the calculation for the other side of the final state cut in SIDIS, as I said in the beginning, I will not show that, then one finds, again, one gets the same type of a Wilson line. And if you combine that, because you have to add up the two graphs, with the previous term here, what you get in the sum, so sketch this here plus the piece we have computed, gives us a Wilson line precisely of the form that I showed you on my on one of the previous slides. It goes from Z, if this here corresponds to the point Z, it goes all the, or better, this should better be, sorry. This should be called Y. So this is the transverse component. This is the light cone coordinate of Y. It goes from Z all the way to positive light cone infinity. And then the other part goes from positive light cone infinity back to the origin, which is where the quark field is sitting, the anti-quark field is sitting. So this is how this full Wilson line arises. And what I will not show you, except very briefly, if you repeat the same thing for Drell-Yan. So this was for SIDIS, and the Wilson line points to plus infinity. It's not difficult to see how that calculation changes in the appropriate place for the Drell-Yan process. Here, this is one of the graphs you have to compute. So if this is again our incoming L, and this here is an incoming momentum, let's call it Q minus K. And that here would be K minus L. That is the assignment such that the photon momentum is indeed Q. Then the Feynman propagator of this off-shell line here is I over Q minus K plus L. Sorry. Again, with the hat for making the collinear approximation plus I epsilon, and following exactly the same steps that I showed you here in the case of SIDIS, you find that this is equal to 1, oh, sorry, I over 2Q minus times 1 over L plus I epsilon. This is what happened between the Drell-Yan and the SIDIS case. In the Drell-Yan, the relative sign between Q and L is positive. In SIDIS, it was negative. And that means in SIDIS, we had the 1 over L plus minus I epsilon. In Drell-Yan, oops, lost the pen again. In Drell-Yan, we have 1 over L plus I epsilon. everything else staying the same. And that is, then it's clear, if you then repeat this type of the argument, looking at the distribution function side, then instead of having the minus sign here, you have a plus sign. And that, after the Fourier transform, gives you a theta function for the other part of the half line. That means then you get an integral not from z minus to infinity, but instead from minus infinity to z minus. And that is why the Wilson line you get in Brillant has this other behavior. It goes all the way to minus infinity, starting from z. So this was quite hard work, and I think at that point we've all deserved a break. So I suggest if there is any immediate question now, you should ask it. Otherwise, we would make a break.
Everything is clear? Well, you have been very clear, apparently.
Thank you. So then let's all take a deserved 10 minutes break and come back at 25 sharp.
Perfect.
Very good. Thank you. I showed you, hopefully I could give you an idea of how such calculations are done, how Wilson lines really arrive from the, or can be seen as arriving from the appropriate approximations of Feynman graphs in this special regime where the incoming gluon polarization is along the light cone direction. I will now again become more sketchy, because to go through the details of the remaining arguments would cost us too much time. But I want to come briefly back to this issue of rapidity divergences. If one takes a closer look at the calculations, there are on top of these integrals that I've discussed here, where we had the integral over all L plus over such an approximated propagator, because that's what really it was. There are other integrals where the integration for kinematic region stops at L plus equals 0. And then the plus or minus I epsilon obviously doesn't help you to make that finite, because here the finiteness came from the fact that L plus was integrated over both positive and negative values. So from such other integrals which come in rather similar way as in the graph I've shown you, we do have a divergence, and that is what is called a rapidity divergence, because it appears for L plus equal to 0. However, as you see, this can happen at non-zero L transverse and non-zero L minus. So it is not a soft singularity, which we would call the case where all components of L have to go to 0. Instead, it's a singularity from the region where the plus momentum goes to 0 at non-zero minus momentum, and that means it's negative rapidity. And that's, as I anticipated before, negative rapidity gluons shouldn't be associated to the TMD of a right-moving hadron. So in order to exclude that region from the TMD and put it somewhere where it belongs, one introduces such a rapidity cutoff parameter, zeta. How exactly that is done, I will not explain here. And in fact, there are different possibilities to technically introduce that parameter. But you can think of it as something that has to do, or whose logarithm has to do with the rapidity, which appears in such graphs. And then the statement, which again I cannot prove here, but only state, if you consider all graphs, especially if one considers real and virtual graphs with such a gluon being cut or not cut, then these rapidity divergences all cancel if one integrates over the observed KT of the parton. And then you don't need that cutoff parameter anymore. And that's why in ordinary KT integrated distributions, we never speak about it. But if you do not integrate over KT, then the cancellation is no longer taking place, and the cutoff parameter becomes essential to get the physics right and to get a finite and controlled answer. Now, again, you might ask yourself, why does he carry us through all these very technical steps with Wilson lines and their staple-like paths? The point is there's actually physics in all this. And that's really interesting. Now, if we come back to this Sivers distribution function I introduced a little bit earlier today, remember, it comes from parameterizing the unpolarized quark distribution in a fixed polarization proton in this way. This Sivers distribution gives us an anisotropy in the PT distribution of measured quantity in CDIS, it turns out. And that effect was actually observed experimentally already a decade ago or so, and it's been confirmed ever since. So there are good reasons, and there were good reasons at the time already, to think that this is a real physics effect. However, if one looks a little bit more closely, the prefactor of this distribution here changes sign under time reversal. And that's a very, very annoying thing. If you have something that changes sign under time reversal, this of course stays the same because it only depends on square here. And if you know that time reversal is a symmetry of QCD, you would conclude, well, this term cannot be non-zero in the theory, and therefore the Sivers function must disappear. But sort of experimentally, that doesn't seem to be the case. So what is the resolution of this puzzle? And that was really a puzzle in the field for a few years. And the answer is precisely in this little but important detail that we have worked out in the last few slides. Time reversal actually doesn't map this function on itself. Instead, time reversal carries us from the Sivers function with the Wilson line as you need it in CDIS to the corresponding Sivers function that you need with the opposite direction Wilson line in Drell-Yan. Unsurprisingly, a time reversal carries you from a plus light cone infinity path to a minus light cone infinity path. So it is not, if this dependence on CDIS or Drell-Yan were not there, then from this equation you would immediately deduce that the function has to disappear. But since these are just two different functions, what you get instead from time reversal is the prediction that this anisotropy in a distribution should have the opposite sign when you measure it in CDIS and when you measure it in Drell-Yan. So that's really a very subtle physics effect, comes from the gauge sector of the theory, quite puzzling. But this is actually, there's a big program experimentally to verify whether that's true, because it means if you know enough about the Sivers effect, say in CDIS, you can predict its sign and magnitude in Drell-Yan. Now, I think it's too early to say that we have seen this firmly in data, because especially on the Drell-Yan side, these measurements are very difficult and have relatively large errors. And also, of course, from any measurement, you cannot easily extract the functions as a function fully of their variables and also of the quark flavor. But I would say even with what we've measured so far, it points into the direction that this relation is really realized in nature. But more work will be needed to make that a definite statement. So let me make just a few remarks about even more complicated processes. And even more processes means processes in which you have colorful particles both in the initial and in the final state. An example is the production in PP collision of a gamma plus the jet. So the jet is part of your hard scattering, like it's sketched here. Or instead of a gamma and a jet, you could look at a pion and a jet. The pion formation would be described by a fragmentation function. In this case, if you look again at the types of gluon exchange you have to take into account, it gets much more complicated. And the Wilson line paths that you get from simple calculations, like the one I showed you, get more and more complicated. So this looks like a whole another complication of parton densities and fragmentation functions with very complicated paths of the Wilson lines. But it's even worse than that. If one goes beyond these one loop examples, which would suggest you what the Wilson lines should look like, one finds that the higher order gluon exchange doesn't actually nicely exponentiate into Wilson lines as you would need it. And that means really you have a breakdown of TMD factorization as I've discussed it here. So this is the state of the knowledge. It was seen already more than 10 years ago. There has been more work since that confirmed this conclusion. We just don't know how to control and establish TMD factorization in processes with incoming hadrons and outgoing hadrons or jets. So that means, unfortunately, that the realm of TMD factorization is limited to CIDIS-like processes and Drell-Yan-like processes. Perhaps there's a few more, but in general, this type of factorization with measured transverse momentum is so subtle that it actually breaks down in many cases. Now, coming to a slightly different aspect of TMD factorization, I want to briefly say how the two types of factorization I discussed today actually are connected. So the low Q2T description in terms of TMD factorization, I discussed most of the time, but I already earlier on today showed you briefly what happens, how you factorize in the case of a high QT. And to understand this, how it comes about, let's first look at the transverse momentum distributions themselves. Consider the case where the transverse momentum of the quark that you extract is much bigger now than a typical hadronic scale. Then how can you expect to find a large KT, relatively large KT, say a couple of GeV parton transverse momentum inside a proton? Well, you can think of that being generated by starting with a lower momentum in the transverse plane and emitting a large KT recoil, and then you are left with a large KT in the opposite direction. And if you turn that into a calculation and a formula, it means if KT is sufficiently large, then you can describe your KT-dependent distribution in terms of a factorization formula. The factorization formula then has the form of a perturbative splitting, which describes this type of graph here, or here coming from a gluon to a quark, times an ordinary usual parton distribution function. These are the collinear ones. And unsurprisingly, this here is the same type of ladder graph we discussed for the D-glub evolution. Turns out that this type of splitting kernel here is very closely related to the D-glub splitting functions. At higher orders, it's a bit more complicated because you have this extra zeta rapidity parameter in the TMDs. So it's not equal, but it's closely related. And the important thing is, purely from dimensional reasons, you can anticipate if this here is dimensionless, this here is dimensionless, then since this here is a density in KT space, its mass dimension is 1 over KT squared. The only dimensional prefactor you can get out of this calculation is 1 over KT squared, and this is in fact what you get. You can rewrite this entire thing in the Fourier transform space, which I showed you earlier is useful. And then you get another kernel now referring to B space. So the logarithms of KT over zeta turn into logarithms of B squared. But otherwise, things work pretty much in the same way. So what we have gained now is a perturbative relation between TMDs and ordinary parton distributions in the range of large KT or of small b. Now coming back to describing scattering processes. Collinear factorization requires that the measured transverse momentum, say in Sidis or in Drell-Yan, is much bigger than a non-perturbative scale of QCD, which generically I can think of something of the order of the proton mass. KT factorization or TMD factorization requires that the measured QT should be much smaller than the hard scale in the process. So you realize these conditions can actually be fulfilled at the same time if you have large enough a window between M and Q. Then you can have a scale which is in between and equally far away from either of the two ends of the scale range. And in such a region, actually, both descriptions should be valid. So if one does that, one should do the following exercise. One should take the KT factorization result, see how it simplifies for QT much bigger than a mass scale. And that's exactly what I discussed here. In this case, the TMD dependent quantities in your TMD factorization formula can be expressed in terms of collinear densities. And on the other end, you should take your collinear factorization result where you had integrated distributions from the start and take everything in the limit of QT much smaller than Q. And one finds very gratifying result that you get full agreement for the unpolarized cross sections. Well, this was known for a long time. You can be more bold and look also at the various spin asymmetries and correlations I've discussed, like the Sivers asymmetry. And one finds also for the Sivers asymmetry, these two descriptions match in the region of common validity of the two regimes. Let me skip over the next few slides and come to a last but extremely important aspect that I want to discuss here. And that's the relation between transverse momenta and transverse positions. Now, if you think of ordinary quantum mechanics and say the Schrödinger wave function for something like the hydrogen atoms, you know that you can write down your Schrödinger wave function in position space or in momentum space, and you go from one to the other just by doing a Fourier transform. However, the same is not the case for KT-dependent distribution functions and for impact parameter distribution functions that Barbara discussed yesterday, and also I to some extent. So why is that? Let's take a look at that. Let's look at, we can look at different quantities. Either we look at the quark field. The quark field naturally sits in position space, but of course you can consider its transverse momentum Fourier transform and have this sort of hybrid field which lives partially in Z minus along the light cone and KT. Or you could do the same type of exercise for physical states, and that's this Fourier relation between impact parameter eigenstates and eigenstates of the momentum, which we used already yesterday. So in both cases, we have one quantity that corresponds to a localized object in transverse space, either the proton or the quark. This really describes a quark sitting at position Z. On the other side of the equation, you have an eigenstate of momentum in the transverse direction, either a transverse momentum proton here or a transverse momentum of the quark. Now, the distribution functions that we discuss all the time are not linear in such fields or in proton states. They are bilinear, and this is where the important point lies. So just consider the product of this one Fourier transform field here for the quark, and then of the corresponding Fourier transformed field conjugate. So this, you can write down the two Fourier transforms in terms of the position space fields. So we have this composite Fourier exponent here, and not difficult to see if you want to rewrite this mixed expression in terms of the sums and differences of the positions and the momenta. This is what you get. So this is just simple algebra. And now you can identify which type of quantities are actually Fourier conjugate to each other in these bilinear quantities. And we see that the average transverse momentum, which would be 1/2 times this here, is Fourier conjugate to the position difference of the two fields here, or it would be the same with the proton states. Whereas the transverse momentum transfer or difference, which is this here, is Fourier conjugate to the average position of the two entities. So that's the first term. And in particular, that means that the average transverse momentum and the average transverse position are not Fourier conjugate to each other because they appear in different lines in this relation. And if you write down the quantities that we're discussing here all the time, this is how it looks like. So if I consider TMB, then as we have seen, and I write down here only the transverse components of momenta and positions. Here we have the fields sitting at different positions and the corresponding and the sort of the difference between this and that position is just Z, and the Fourier conjugate to that is just our common transverse momentum here. For impact parameter distributions, it's the other way around. Here, the fields sit at the same position, but there is a momentum transfer for the proton eigenstates. And if you make a Fourier transform with respect to that, then you get the impact parameter distributions discussed yesterday. So these are really two very different quantities, and they are not the Fourier conjugates of each other. And that naturally comes from this discussion that we've done here. And that's really very different from what you would have for a wave function. So the underlying statement here just is that wave functions and squared wave functions or distribution functions behave in very different ways in this respect. So this here just repeats the same statement. And you can actually have both types of differences at the same time. And these are the generalized TMDs that Barbara has, I think, already hinted at yesterday and will certainly speak about more in her lectures, where you can have momentum difference here between the external states. And at the same time, you can have the fields at different positions. The Fourier transform gives you then the average transverse momentum on the left and the right. So you would write that in this symmetric fashion here. And if you also make the Fourier transform of this quantity with respect to the delta, then you get what is called the Wigner function, depending on an average position B and an average transverse momentum K. So you can then draw this kind of inheritance graphs, which also Barbara showed you some version of yesterday. I will not walk us through this in any detail. The only point I want to emphasize is that when reading these graphs, there is some care needed in a few points. And that is when you have the relation between a KT unintegrated and a KT integrated quantity. Because, as you know, the KT-dependent distributions don't follow D-Glab equations. These distributions do follow D-Glab equations. This here, however, has a rapidity parameter and a Collins-Soper equation associated with this. This one doesn't. So in that sense, it's clear that integrating this here over KT, giving you that, is too simplistic. And in fact, you can understand also in a more direct way why it is simplistic. So this is the naive relation that is suggested by this kind of graph, and which I also gave you in the beginning of today's lecture. But now we know why this cannot work. Because a few slides ago, I showed you that at large enough KT, the quark distribution behaves like 1 over KT squared. You try and integrate that over all KT squared, you realize, oh, that's a logarithmically divergent integrals at large K. So certainly this here cannot hold literally. You could correct it using a cutoff. So then you would say, well, integrating KT up to a cutoff gives you the ordinary part quark density at the scale mu. This is actually this simple physics idea that we discussed when we first discussed evolution in the D-glub sense. And sometimes that's even used in the literature. A different way of looking at regularizing this integral is rather than a cutoff, you can also multiply this with a Fourier exponential. If z is of the order 1 over mu, then this oscillating factor will suppress the region of very large K, just because then the exponent oscillates back and forth and gives you a finite result. And from that point of view, if you take the Fourier transform of your KT-dependent distribution with this exponential, and that's what we introduced anyway, that gives you back the collinear distribution plus corrections of order in alpha s. And that's exactly this kind of perturbative relation we also discussed here from a different point of motivation. So that means these type of schemes retain their relevance and value, but one should be aware of the fact that the arrows with d squared kt really come with quite a bit of small print, which, however, is fully understood, and therefore you can continue to use this. So this brings me to the summary of the TMD lecture. TMD factorization is really a new type of factorization compared with the ordinary one, has important differences, that different evolution equations. And it's a case where the physics that is sitting in Wilson lines is actually really quite surprising and subtle. And thinking that you can get rid of the Wilson lines just by taking a plus equals 0 gauge it would be a big mistake. Unfortunately, TMD factorization isn't quite as universal in its field of application. But sometimes it is valid. And it's even nicer that we have, when it is valid, we have a smooth transition for the theory description between low and large measured transverse momenta. And if you're interested in the transverse momenta of partons inside a hadron, then the TMD formalism gives you a theoretically controlled way to speak about this degree of freedom and to learn about it from measurements. So that brings me to the end of this lecture. Are there any questions?
Well, since this is the last lecture by Markus, I would kindly invite you to ask questions if you have.
I still have a little bit about double parton scattering for a few minutes.
I know, Markus, but at least.
But before, if there's any question on this part, of course, yeah, we should ask it now because I would have to switch slides.
Can I ask a question?
Yes, please.
So before, when you talk about the scale dependence of TMD, yes, you say that the TMD depends on two kinds of scale. One is rapidity and one is UV scale, right?
Yes.
And so I'm wondering, so is that UV scale the same as the UV scale of the PDF?
No, in fact it isn't. Thank you for the question. I forgot to say that actually. So I motivated to some extent that there is a rapidity dependence here and an associated evolution equation. So how does this evolution equation for the renormalization scale appear? Especially since I told you there is no deglap equation for the TMDs. The reason is, now I'm trying to look for a suitable graph. If you look at this type of factor here, because this is what pictorially is your TMD. If you think there is a final state cut somewhere here, and you're not allowed to have any large momentum going across the final state cut, that is what removes the deglap evolution. But what you can still have is that you have to the left or to the right of your cut virtual corrections. And virtual corrections are never restricted in the loop momenta because there is no momentum conservation that would restrict the loop momenta. And that kind of thing has ultraviolet divergences which need to be still renormalized. So the renormalization of these ultraviolet divergences in virtual graphs is what gives you the evolution equation in the renormalization scale for a TMD. And the fact that they are virtual corrections and don't mix partons with different x values is why you don't have any x integral as in the deglap equations. Remember, in the deglap equations, we have actually in the splitting functions terms that also come from virtual corrections, like this here. In the deglap equations, that gives you a part to the evolution kernel, which comes with a delta function. And in this case here, since everything comes with such a delta function, you just carry out the x integral and you have an ordinary product.
Okay. So, so in this way, even though we still have this kind of you will how to say scale dependence of TMD, but this dependence, this evolution equation don't go back to deglap equation after we get the integration over K-perp, right?
Indeed, yes. Where the deglap equation comes in is in this more subtle way. So that's another way of seeing things. We have this, it's also sometimes called this matching equation between a TMD on one side and the PDF on the other side. The mu dependence of the TMD is via this simple anomalous dimension gamma f. The mu squared evolution of the PDF on the other side is the deglap equation. And that means in order for the right and left-hand sides to be compatible, this kernel here starts at order alpha s. The scale dependence of this kernel here has to compensate the deglap part of this mu dependence and give you the gamma f part of that mu dependence. So the transition from one type of evolution equation to another type of evolution equation is precisely sitting in this matching kernel here. And this is how things are consistent again.
So you mean that this connection is not in between, how to say, the high Qt described, how to say, fragmentation, that part, right?
Yes, indeed. You can see it explicitly in this matching regime where b squared is small. The evolution equation for this here are also valid if b squared is large, but then we lose the connection to the integrated PDFs. Yeah.
Okay, thank you.
An integrated PDF and a TMD is a connection that we can make explicit at small values of b squared, which, as I discussed in the last slide here, is another way of saying, well, taking this here at a small value of b, or of z as I call it here, is something like a cutoff of the full KT integral.
Okay.
And
thank you.
That subtlety is why in this kind of diagram, you can have one type of evolution equation between this and another type of evolution equation for that factor. It's just because this integral over dkt squared is much more complicated than the simple here suggests.
Okay. Okay, thank you. Okay, thank you very much. I think that's very helpful.
Thank you.
Okay, Markus, please go ahead a little bit.
A little bit. Well, I think we shouldn't run over time too much, but perhaps I can just give you a very, very rough idea of what double parton scattering is about.
Well, what does Barbara think about? Can we?
Sure.
5 minutes.
No problem. No problem.
5 to 10 minutes.
Thank you, Barbara.
Yeah. So let me jump right into the subject. This connects to a discussion we've had earlier in the lecture regarding proton-proton collisions in factorization. As I emphasized at the time, factorization formulae, something like the single Drell-Yan process, are inclusive, and you're not supposed to ask what happens with the spectators in detail, because in detail the spectators will do things. They will scatter on each other. And in going from this sketch to a graph, you could have the hard scattering for the Drell-Yan case, and another scattering, which, for example, in this case, gives you a dijet. Now, you can turn this here into part of what you want to measure. And on the condition that this is, again, a hard scattering, you can think of this as, well, two hard scatterings taking place in the same PP collision, which is what is called double parton scattering. And the idea now is that you can try and see, do we have a similar factorization type for this as we have in the case of a single hard scattering? And the answer is yes, you do. Let me skip over this and right away give you an example of where this double parton scattering is important. Think of the production of two W bosons with the same electric charge. Turns out, easy to see, you cannot produce a spin, a charge equal 2 system starting from a quark-antiquark annihilation without radiating anything into the final state, simply because it's impossible for the charges. So the lowest order for producing two like sign W's in a single parton-parton interaction starts at order alpha S. You have two factors of G in the amplitude and therefore two factors of alpha S in the cross section. However, if you make one W in one quark-quark annihilation and another one in another annihilation, there is no penalty of alpha S squared. And in such a case, you can expect that this normally rather suppressed double parton scattering mechanism might actually be visible. That was predicted quite some time ago in this paper here. So the thing to point out is this was the computed cross sections for gauge boson pair production computed with single hard scattering. So you see for opposite sign W's or W's and Z's, these are very large cross sections compared with the estimates for the double parton scattering cross sections in the same charge channel, which for opposite sign W's is this upper curve. However, the estimate for like sign W's was very close to the estimate of like sign W's from single hard scattering, which is the green curves. And indeed, just a few years ago, this process here could be measured experimentally at the LHC. So, cutting a long story short, I just want to give you an idea of how one gets to a factorization formula in this case, also because it really ties on to the machinery I've discussed earlier today. So let's consider the case of two gauge bosons produced, one by a hard scattering and the other by another hard scattering, both coming from the same proton. it shows always, it's useful to have a symmetric assignment of the momenta in this big graph. So K1 for the first hard scatter is the average transverse momentum averaged between the initial, between the amplitude and the complex conjugate amplitude, and 1/2 times R is describing the momentum difference on the two sides. The same happens in the second hard scattering, where the momentum difference just has the opposite value because I want this to be symmetric. So this is my assignment of variables, and I do the same thing for the proton on the other side. And the important thing you can see here is that this momentum difference here between left and right in the first proton and in the second proton, by momentum conservation, they have to add up to 0. That comes from the fact that when you add up these two momenta, you have to get the momentum of the observed boson, and that is the same that you must get when you add up those two momenta. So what does that tell us? Well, it tells us if you consider this type of graph, you make the same type of approximations as we normally do. For right-moving particles, you neglect the minus components. For left-moving particles, you neglect the plus components. You find a cross-section formula in which you have a double parton distribution for one times the double parton distribution for the other proton, and they are evaluated for certain values of the transverse momenta and for opposite values of this momentum mismatch between the left and right-hand side. Now remember what we discussed just a few minutes ago. If you have a momentum difference between the left and right-hand side of such a distribution, and if you make a Fourier transform, you get a position, which I call Y here, and that position represents the average position averaged between left and right-hand side of the graph of the parton. So this here is for the case of two parton, again, the same idea that one is using for these Wigner functions in the one particle case. You have a mixed representation in terms of transverse momenta averaged between the left and right-hand side of the graph, and transverse positions averaged between the left and right-hand side of the graph. And the physics interpretation that you get from this, and it's really specific, it's the position of quark fields, it's not just some physical intuition that you pull out of your head. The physics interpretation of this distance y is it's the transverse distance between the two hard scattering processes. And that's very nice because it gives us, on the one hand, a valid type of factorization formula. And on the other hand, it comes with sufficient physics intuition to think about it. So if one does a lot of extra work, one finds that indeed for double parton scattering, you can again formulate factorization in which you have one parton level cross-section for the first hard scatter, another for the second. These are exactly the same hard scattering cross-sections you would compute in the case that there is just one hard scattering. They don't know about each other. The place where the two protons know about each other is this convolution of two double parton scattering, two double parton distributions. And here you have this integral over the relative distance between the first and the second hard scatter. You can do the same thing if you measure the transverse momentum of the final state distributions, of the final state bosons, and then you get a natural generalization of the TMD factorization formula I showed you earlier with Fourier transform with respect to the two observed transverse momenta. And here you have the TMD analog of a two parton quantity with Zi being the Fourier conjugates of the transverse momentum Ki. And that's all I wanted to say. There's much more you can do then once you have this theoretical formalism. If you're interested, you can look yourself at the following slides, but I think it was more important today that we discuss in detail and understand the TMD part of the lecture. So that brings me to the end. If there's any more questions, now is your chance to ask it. Otherwise, any other question about TMDs, I'm sure you can also ask Barbara later on, because she will come back to the topic.
So let me ask something about double particle scattering.
Yes, please.
You would say that the factorization, the proof of factorization for DPS now is as solid as it is for DIS or for CIDIS, or? I
would say it is as solid as the one we have for single Drell-Yan production, because that is the closest analog. There is really no double parton scattering analog for DIS, but the analog is with Drell-Yan.
Right.
And in fact, the factorization proof for Drell-Yan is already more complicated than the one for DIS, because in Drell-Yan we have to show what to do with these spectator interactions. And of course, you have to do the same thing for double Drell-Yan, but it turns out that if you understand the single Drell-Yan case well enough, you find that the double Drell-Yan case allows you to reuse the same type of arguments, some form of unitarity. Whatever the spectators do doesn't matter as long as you're not interested in the details of what they have done.
Yeah. Thank you. More questions for Markus about any lecture we had before, eh? If you have curiosities or something which is not clear.
You have a question about this very last slide. My question is when does the finite radius of the proton can play a role?
I'm sorry, you are very hard to understand.
Okay, sorry, I try to speak louder and closer to the microphone.
Yeah, get closer to the microphone. I think that will help. Thank
you. When can the finite radius of the proton can play a role in this issue of double parton scattering and in this Fourier transform in the transverse plane?
It does in fact play a role, because it basically has its imprint in the dependence of these double parton distributions on Y. Y is roughly speaking, is the distance in the transverse plane between the two partons that you extract. That distance cannot be much bigger than the proton size itself, because the proton at some point stops having anything that you can scatter on. So you could say the characteristic length scale of the Y dependence in these functions is given by the proton radius.
Okay, thanks.
And if you take the slides and look a little bit further on, there are some comments on that, in fact, where you see that the overall size of the system does have some importance.
More questions? Which is your opinion? You think that thanks to the operation of high luminosity LHC, it will be possible to extract the double particle distribution functions to a given accuracy? Just a parameterization like the look array for the parton distributions.
I don't think we will be able to play the same games as we can for PDFs. And the reason is mainly combinatorics. Yeah. You have so many more different double parton distributions because you have so many combinations of two partons. They depend on many more variables. So I think even with very, very good measurements from the LHC, we will not have enough data to make a fit which has hundreds of parameters. And before we even could speak about the parameters, we would know what are good functional forms.
Right.
So I think the name of the game there will be different. One will have to make physically motivated models or Ansätze for these distributions, and then see how they compare with data. Yeah, because in that direction you can always go. But I think the necessity of constructing physically motivated good models is much bigger here than it is for parton distributions, where as soon as you have a good ansatz for these one-dimensional functions, you can just fit them. Yeah.
I see. That's good for us. Yeah.
I think that is the way it will go. Sort of in between the two extremes, in a way, you might think things will happen for generalized parton distributions. Yeah? GPDs depend on 3 kinematic variables, but at least you don't have as many flavor combinations as you have for double parton distributions.
Right.
So for GPDs, I think there again, you cannot just hope to make an ansatz for a 3-dimensional function for all the partons and determine all these parameters in a fit to data. But the complexity in that case is not quite as high, or the combinatorial number of functions is not quite as high as in double parton scattering.
And then they get one-body quantities after all. The double distributions are 2-body quantities. So I mean,
and for GPDs, we have constraints like the sum rules, connection with form factors, and such. So I think the GPD case is somewhere in between.
Thank you. Very important opinion. More questions, comments, whatever. Well, if there are none, I would thank very much Markus again for these bright lectures, and we hope to welcome him in Florence one day when it will be possible.
Yes, that's always so. Thank you very much, and thanks to all in the audience for your questions during this lecture series. So now have fun with Barbara's lectures, which you will see will to a large extent deepen many of the things I could only touch.
Very good. Thank you again. Bye. Bye-bye. Barbara.